You take any circle and you connect the points A, B, C, D, 4 points on the circle. If they form a quadrilateral, they're going to have this relationship where the product of the opposite side lengths, the sum of the product of the sum of those product lengths are going to be equal to the product of the lengths of the diagonals. That seems way too good to be true, but circles have a lot of interesting surprises with them. We're going to go to a blank spot. I'm going to prove this, and it's such an elegant little proof that I think it's worth going over. So would you make a circle on a blank page? And I probably should make this a little smaller. I'm going to make it about this big. That's good enough. And then we're going to make some lengths. We're going to go from here to here, here to here, here to here. Did not want that to be super regular looking. That's better. And we'll label these A, B, C, and D. All right. Now, the next thing we're going to do is we're going to connect diagonals AC and BD. But we're going to do something really strange. We're going to call this angle theta 1 here. And what I'm going to do is I'm going to draw a line segment from A over to BD, A over to BD, so these two angles are the same. And this is going to land at H. Whole key to this is drawing that. So we're going to, first thing we're going to do is we're going to draw AH, so theta 1 equals theta 2. And then I'm going to locate some different angles. I'm going to locate this angle here, alpha 1, and this angle here, alpha 2. Tell me about those two. Really? Why is that? Yep. Alpha 1 is equal to alpha 2, both subtend arc what? AD. Okay, so that's good. So theta 1, theta 2, alpha 1, alpha 2, those are equal. What can you say then about triangle? Say about triangle ADC and triangle, let's see, what's that going to be? AHB. What can you say about them? This is bothering me. I must fix it. Okay. They're what? Are they congruent? They are equiangular, or you can say similar. But if those two, theta 1, theta 2, alpha 1, alpha 2 are congruent, then this third one will have to be congruent too. And by the way, when you're starting out in geometry, they have to prove that. We kind of skip that. If two of the angles are congruent, the third's going to be congruent. The triangles are equiangular. So if they're equiangular, here's the punchline then. AB over what? What's the longest side on ADC? AC, yeah, is going to be equal to the ratio of BH, it's across from theta 2, so going to be BH is to what? Yeah. DC. Yep. And we can do a little algebra there. Solving for BH. BH is just going to be AB times CD all over AC. So far, so good? You probably guessed we're halfway there. Okay. Now what we're going to do is we're going to look for some more angles here. Look at angle AHB. Nope. AHD. What is this angle in here? What's that angle going to be? It's not 2 alpha. Let's do this. This angle here is 180 minus what? Theta 2 minus alpha 1, right? So what would this green one have to be? Theta 2 plus alpha 1. Yeah. So I'm going to take this out here just because it's too much. Okay. And let's see, what's the other angle that I want to get to? Okay, so I'm going to write that down. This is where it's a little hard to write here. So this is angle AHD is equal to alpha 1 plus theta 2. And you can explain that as an exterior angle theorem to triangle A, B, and H. Just to remind you of that one. This is a good time to remind you of that. If these two will be equal to this one in green because those two have to be 180 minus to get that, and that's the supplementary. All right. Now I need to put another theta in, and I'm going to put it right here, theta 3. What can you tell me about theta 1 and theta 3? They're the same. So theta 1 equals theta 3. Why? Subtend arc DC. Both subtend arc DC. Okay. And we can also say, of course, that if theta 1 was equal to theta 2, these are all equal to each other then. Theta 1 equals theta 2 equals theta 3. And with that in mind, now what we can do is we can say that did we say beta 1? What can we say about beta 1? I haven't put beta 1 up there yet. Here's beta 1, and here's beta 2. What can you tell me about those two? They're equal subtend arc AB. Both subtend arc AB. All right. So these two are equal. This one all right. Thank you. Okay, so a little hard to see here, but we're doing our very, very best here. We're going to have this angle here is alpha plus theta. This angle here is alpha plus theta. And we've already shown the alphas are equal and the betas are equal. So if those two are equal, then we can say that triangle AHD is equiangular with ABC. Whew. That's a big challenge, but these are subtending AB. These two are going to be equal to each other, so now they have to be equiangular. If they're equiangular, now we can do our final fun thing here, and that is that HD over BC, so let's take a look at that. HD is to BC, okay, as what? HD is to BC as AD. AD is to what? Yep, AC. AD is to AC. That's right. Now substitute, solve for HD this time. And so you're going to get AD times BC over AC. Well, that's horrible. Now, watch this. Now what we've got is this guy, BH, which is here, and we have this guy down here, HD, which is here. What does HB plus HD equal? The diagonal BD. Perfect. HB plus HD will be equal to BD. So now we just go ahead and add those together. HD, let's see, BH was AB times CD over AC, and HD is ADBC over AC. And that should be equal to BD. Now, normally we'd be done, but this is further math. We're not done yet. AB times CD plus AD times BC all over what? Common denominator, AC is equal to BD. So what is AB times CD plus AD times BC equal to? AC times BD. And going over this one more time, this was A, B, C, D. AB is this length, CD is this length. Opposite, AD, BC. Those are opposites. Then what's AC and BD? The diagonals. Do you like that? I could tell. The answer is yes, I like that. But if not, let's just do some simple problems then. The proof was like the killer of this part, but the problems are not that bad. So for this one, you've got this quadrilateral. They're asking for what's one of the diagonals, AC. So you just go AC times diagonal BD. BD is 12. is going to be equal to, and then you just do any pairs you want. AD is 10 times BC is 5 plus AB is 6 times CD is 9. So you're going to go AC times 12 equals 50 plus 54. You're going to get AC is equal to 104 over 12. Great. Converse is if you do this product and the sum of the product of the opposite sides is equal to the product of the diagonals, then what can you say about ABCD? They're cyclic. Yeah, and we would say concyclic because it's an inverse. So we're going to check this. Is ABCD cyclic quadrilateral? Let's double check. So AC, they're saying AC is 10.5 and BD is 8.2. So 8.2 times 10.5 should be equal to 7.4 times 9.2 plus 3.4 times 5.3. And if you help me out here, get your calculators out. Is 8.2 times 10.5, that's going to be 86.1. But would you take your calculators, tell me what this product and this product are? Oh, they've got it here, 10.5. What do you get? 7.4 times 9.2. Can somebody give you that real quick? 68.081. And then plus, what's 3.4 times 5.3? I'm hoping around 0.02. So that should be 86.1 equal 86.1. Thank you. And so if those products are equal, then ABCD is a cyclic quadrilateral. You like it? So kind of easy to apply. You try this number 1. And that's it for the video today.